for tokamak is that hot fusion brings them together using high energy, and they smash into each other, and the product splits apart immediately into two fragments. That's hot fusion.
Am I correct? I asked a question to Solar Turbine down there in San Diego, because they were selling components for nuclear reactors, and we got into this discussion about capacitors. Is it correct that they take basically a high voltage discharge from a capacitor and hit the uranium logically, electrolytically, to get it started? Is that how they get it started?
No. A capacitor is used to store energy, which can then be used to trigger a fusion reaction.
That's what I'm talking about.
Yeah.
That's what I said. Is they have a super fast capacitors, and they're discharging them onto the uranium rods to start the reaction.
Not uranium. There's no uranium involved in fusion.
Okay.
That's a fission reaction. That's entirely different. Fusion reaction uses only a gas, deuterium gas, or tritium gas, or hydrogen gas. There's no uranium involved.
No nuclear.
It's nuclear, but it's not uranium.
Okay.
See, there's two different kinds of nuclear reactions. There's the fission, which is uranium that splits apart into two smaller pieces. That's what ordinary nuclear reactors do. And fusion, where the two smaller pieces come together to make a bigger piece. And that's fusion.
Okay.
And the two smaller pieces are hydrogen isotopes. The two bigger pieces are plutonium, uranium, thorium, the big atoms.
Right.
All right, so to split those apart, that's fission. That's where we get our energy now. The other end, fusion, hydrogen, that's what we're trying to get energy from right now. And the technique they're using is called hot fusion, which brings them together. See, in order to bring two atoms together, they both have positive charges. In order to bring two nuclei together, they don't want to go together because they both positive charges.
They're trying to force a couple magnets.
You have to force them together, and you do that by imposing a tremendous kinetic energy. So they come into each other at very high velocity, smash into each other. That all becomes a Coulomb barrier. They fuse. They give off a huge amount of energy. The product then splits, goes off, carries the energy with it. That's hot fusion.
Okay.
That has to be done in a magnetic bubble because it has to be so hot that there's no anything solid. So it's done in a magnetic plasma configuration. Cold fusion, on the other hand, is different.
Let me ask you a question before we go to cold fusion. In that reaction, is it radioactive? And if it was out of that cell, if it could be escaped outside that bubble, would it be radioactive enough to kill you? Is it a different radioactivity than fission?
Yes. Fission makes a whole variety of radioactive fragments of the molecular atom.
Okay.
Fusion makes only one radioactive product, and that's tritium.
Okay.
And tritium is a beta emitter and has a 12-year half-life, and it's generally speaking not very biologically dangerous.
Okay.
But that's the only radioactive product. But you get a lot of neutrons and you get a lot of secondary radiation produced, but the primary reaction does not produce much in the way of radioactivity.
Thank you for explaining to me that way something that's in there. It's not like I get it.
Okay. Now, cold fusion is different. Cold fusion is new. Cold fusion occurs in a solid at room temperature. Doesn't require this huge energy. Doesn't require the magnetic bubble. All it does is require a special condition within a solid material. And when it occurs, the two deuterons come together and they make helium. They don't make tritium. They don't make anything bad. They make helium. There's no radioactivity associated with it. That's the beauty of it. And it makes a huge amount of energy when it does that. People are trying to figure out how it goes about doing that. It clearly does it. The evidence for it doing that is overwhelming. And you can do it a whole bunch of different ways, not just the way that Margaret Fleischmann initially discovered.
Thank you for clarifying that.
Okay.
because that's what my kind of understanding was. Palms and freshmen did it one way, but there's maybe other ways that this could.
Yes, there are other ways. There's 5 ways altogether that this can be done. And so you get heat energy and you get helium. Now, if you have some light hydrogen present, you can also get tritium, but you don't have to get tritium as a secondary reaction. You can also get what's called transmutation. The hydrogen nuclei will go into a larger nuclei and move up the chain. That can also produce some radioactivity, but not very much.